this is Calculus 12, Chapter 2.3. We're going to look at some extra things that might help you with the homework. We're going to look at proof by contradiction. We need to consider the opposite and show that this leads to a false statement. And we can conclude the original statement is true. So I'm going to let you think about this and work on this, and I'll use this as an example. This is easier than this. And if you get stuck, then you can look at the proof. Show that square root 2 is irrational. So we assume that square root 2 is rational. We assume the opposite. So if square root 2 is rational, we can represent it by a over b, and a over b are integers, and it's expressed as a fraction in the lowest terms. And we can square both sides to get rid of the radical sign. Now we have a squared over b squared. We do some algebra. A squared equals 2b squared. If we have 2 on this side, that must mean a is even, because an even squared will lead to an even, an odd square will lead to an odd. And this must mean that b is odd because we have a over b in lowest terms. It must be odd because if we had a and b both even, we could cancel out a 2 and it wouldn't be in lowest terms. So next, let a be equal to 2c because we know that a is even. So we substitute. And when we expand this side, we get 4c squared equals 2b squared. Now we have 2c squared equals b squared. So with this substitution, now we conclude that b must also be even. However, we've already said b is odd. So b cannot be even and odd, so this leads to a contradiction. And if we use Latin, this term is called reductio ad absurdum. So that's proof by contradiction in Latin. So this is a contradiction, so square root 2 must be irrational. We say the opposite of what we assumed. And we say QED, quod erat demonstratum. I haven't spelt this out before. Quod erat demonstrandum. Now, if you've taken the time to try to solve this one, and you can't get it, let's go through the proof. So assume that there aren't an infinite number of whole numbers. So let n be the last one. Okay, so there must be a last whole number. But by counting principle, we can have n plus 1. So our original assumption is false. Therefore, there are an infinite number of whole numbers. Okay, let's look at another problem. Show that square root 7 exists. Okay, so we have x equals square root 7. We need a function. Now the note here says we can't use square root as a function because that is what we are trying to prove, so we must use a polynomial. So we have x squared equals 7. We square both sides. So now our function equals x squared minus 7. We have n equals 0. We need an a. So we need an a that will give us something less than 0. Let's use 1. Use an easy number. B. We need something that's going to give us positive. 2 won't do it, so we'll use 3. So f of 1 equals negative 6. 1 squared minus 7. F of 3 equals 3 squared, that's 9, minus 7, that's 2. F of 1 is less than n is less than f of 3. F is a polynomial. Therefore, it is continuous. We need this to invoke IVT. So, by IVT, there exists a C between 1 and 3 such that f of C equals 0. And that's how we use IVT. And that completes this short lesson.